Good day, everyone. Today we'll be presenting our project titled Improving Battery Thermal Management with Phase Change Materials. Lithium-ion batteries are widely used in electric vehicles and energy storage systems, but their performance and safety are highly sensitive to temperature. When batteries overheat, efficiency drops, lifetime shortens, and in extreme cases, thermal runaways can occur. Traditional air or liquid cooling works, but it requires fans, pumps, and extra energy. So our goal is to design a passive energy-free and uniform cooling solution, one that can keep batteries safe without consuming additional power. To address this, we propose using phase change materials as a passive thermal regulation layer. PCM absorbs large amounts of heat when it melts, keeping the cell's temperature within a safe range, typically between 25 and 45 Celsius. Unlike air or liquid cooling, PCM has no moving parts, needs no external powers, and can be easily integrated between battery cells. This means our designs can reduce both energy loss and system complexity while improving temperature uniformity and safety. This diagram shows the overall heat flows from the battery cells through the PCM layer and then finally to the environment. The battery cells is the main heat source in the system. All generated heat first flows outwards from here. The PCM fills the space between cells and absorbs heat during the melting, helping to keep the temperature stable. At the outer interface, the PCM releases the absorbed heat to the surrounding air through natural convection. Finally, the heat is dissipated into the environment, completing a passive, power-free cooling pathway.
First of all, we developed and validated a thermal management model using PCM within MATLAB Simulink. The goal is to analyze how PCM affects temperature rise, heat absorption, and peak temperature suppression compared with a normal battery cell without PCM. The equivalent specific heat method is used, where the PCM's latent heat is represented at a thermal mass block with a 1D lookup table for CP, coupled thermally with the cell and environment. This allows us to capture the phase change process. When PCM melts, it absorbs a large amount of heat while maintaining nearly constant temperature. For the key results, here we can see the temperature evolution curve averaged over different ambient temperatures. You can see that the PCM case rises much more slowly, and a clear plateau appears around 40 degrees, which is where the PCM begins to melt and absorb heat. Overall, the average temperature is about 10 degrees lower than the no PCM case under static conditions. So, this confirms that PCM can effectively delay the temperature rise and smooth the thermal response. Next, let's look at the heating rate comparison. Before phase change, the heating rate was approximately 0.055 degree per second, but once we reach the melting region, PCM drastically reduces heating rate to nearly 0.005 degrees per second, indicating strong heat absorption. That means the PCM is actively absorbing latent heat and buffering the temperature rise. After the PCM fully melts, the rate goes back to the baseline, which matches physical expectations.
Now looking at the peak temperature, without PCM, the maximum temperature reaches about 135 degrees, which is quite high. When PCM with a melting point of 40 degrees is used, the peak drops to roughly 150 degrees. Among all the cases, PCM with melting temperatures between 40 and 45 degrees performs the best because that range aligns perfectly with the cell's main heating trajectory. Finally, its plot overlays all temperature curves at 35 degree ambient. The dashed black line is the no PCM case, showing a continuous exponential rise. The PCM curves, especially those with Tm near 40 degrees, show a clear flat plateau between 35 and 50 degrees, which corresponds to the latent heat absorption phase. After the PCM finishes melting, all curves merge again, showing that the PCM provides a reversible and transient thermal buffering effect. In other words, it shows the heating when needed but doesn't permanently alter the temperature trend. Overall, PCM offers a simple, passive, and efficient way to improve battery thermal management without any active cooling system.
The second part focuses on the battery heat generation and cooling performance analysis. In this part, we compare 3 cooling methods: no cooling, air cooling, and PCM cooling, on the 3 discharge conditions 1C, 2C, and pulse. The goal was to evaluate how each cooling strategy influences the temperature rise, peak temperature, and overall heat exposure of the cell. Let's go to result and analysis. First is data overview. Here is the summary table. You can see that the no cooling case leads to extremely high peak temperatures, up to 684 degrees Celsius in the 2C discharge, which indicates severe thermal runaway. Both PCM and air cooling reduce dramatically to below 90 degrees Celsius. In other words, both methods are effective, but PCM achieves slightly lower peak temperature and better stability. Next part is average heating rate comparison. From the picture, we can see without cooling, the heating rate during the 2C discharge spikes to 0.35 degrees Celsius per second, which is extremely high. When PCM or air cooling is applied, this drops to about 0.05 degrees Celsius per second. That means both systems effectively limit the rate of heat buildup, but PCM provides smoother thermal buffering without active airflow.
Now let's begin Part C, peak temperature comparison. This bar chart shows that under no cooling, the 2C case exceeds 618 degrees, an unsafe condition. By contrast, both PCM and air cooling keep the peak below 19 degrees, with PCM being just a little better. So, PCM provides comparable protection to active cooling, but without extra energy input. Let's look at the transient temperature curves. For 1C discharge, the PCM curve shows a smooth and controlled temperature rise, with a small plateau around 14 degrees, while the PCM starts melting and absorbed heating. In the 2C test, the no cooling curve rises sharply and runs away after 1,500 seconds, while PCM and air cooling remain stable below 19 degrees. Under plus discharge, PCM effectively damps the rapid temperature oscillations caused by current pulses, maintaining much smoother behavior than air cooling. In short, PCM offers a simple, efficient, and reliable solution for keeping battery temperatures under control.
From a customer's viewpoint, this means longer battery life and better safety, without needing active cooling hardware, lower operating costs since PCM uses no extra energy, simpler maintenance as there are no moving parts or pumps. For manufacturers, PCM offers a cost-effective and scalable integration path for future battery packs. To conclude, our PCM system provides a passive, low-cost, and reliable thermal management solution. It keeps the battery temperature safe, improves efficiency, and extends lifespan, all without external power demand. In future work, we can optimize PCM geometry, explore hybrid PCM air systems, and validate the model with experimental data. In short, PCM cooling makes batteries safer, smarter, and more sustainable. And that's the end of our presentation. Thanks for listening.